Good morning, and many thanks for organizing such a well-run conference.
Okay, thanks.
I'm very happy that you have the opportunity to present our experimental results, even at 3 o'clock in the morning here in Switzerland. I'm a retired professor of chemical and bioprocess engineering, as well as former vice president of the Zurich University of Applied Sciences. Our team of experienced engineers from different fields has been experimenting with LENR over 10 years now. We have been triggered by the Lugano report and the discovery of the hydrogen or gas solid system in Italy and the publications in the physics journal, which is on 1994 and 1995 of the late Professor Focardi and co-authors. I summarize, I put my speech into 4 parts: LENR reactor, experimental results, so it's all in the view of engineers, and then the conclusions.
Excuse me, are you sharing your desktop? Oh yeah, we can see now.
Is everything okay?
It's okay.
The reactor is an upright position because this has 2 advantages. We have a wet reaction zone with induction coil and the reaction material, which can be powder, or now we have nickel rings surrounding a central tube with freely movable K-type thermocouples, and the cold flange where we can exchange the material, and which has feed-throughs at room temperature. That is very important. And the vacuum and gas supply is only used for the conditioning phase. During the operation, it is not necessary. We have also a feature which is not shown here, but I can make reference to the report of Jacques Ruyer, where he discussed the low-loss calorimetry. Actually, you have a dynamic insulation which is working in the same. It is all presented, written in this patent application. Then we have the power supply, an AC-DC converter controlled DC for the power oscillator, and of course the measurement and control equipment based on PC. Then inductive heating and stimulation has the advantage that we have no wiring in the hot section, and excitation leads to very high magnetic fields and current densities, local densities, and this coil has a dual function, process activation and heat extraction at the same time. And with this setup, we can also do calorimetry with this coil type, hollow coil. We have a rough estimation of the energy output, but with this dynamic insulation, we have an exact calorimetry. That is very useful means. I come to the experimental results. I have 4 types of results: temperature effect, excess heat, and the morphological changes, and element changes. I come to the point A, repeatable temperature effect. That is a strange diagram which is repeatable many times. So this is the 3rd run of long testing series with nickel palladium plated nickel foil, and the striking point is this. It can be triggered by pressure decrease. So we see it here, and you see it here and here. As soon as the pressure goes below 100 millibar, then the temperature rise starts, and we can, at the same time, we can stop it, controllable anytime and repeatable many, many times. And it is stopped by H2 pulse for in the order of 300 to 500 millibars. Also here you see we have a pulse. Here a pulse, and the temperature comes immediately within minutes down to the original level. The DC power is, so this axis is the temperature, and the red curve is the temperature. Here we have the duration of the experiment. You see that's quite a long time. And the green line is reported to this, on this axis, that's the H pressure. And a very strange thing is this kink, that the temperature reaches somehow an equilibrium state, but the question is, what equilibrium it is. Then we'll have a closer look on two parts, so the first and the end effect. Here, magnifying a bit, we have a temperature increase of 80 K, and here we have a temperature increase of 120 K. And another strange phenomenon is this sudden temperature pressure increase, and the pressure increase starts spontaneously. You see that is about 3-4 days, and 24 or 50 hours after establishing this constant temperature. Also here, after some many hours after the set-in of that constant temperature, we have this increase of pressure, and it is really repeatable. It's increasing with time and temperature, the rate of this development of some gas. Then I come to the number B, excess heat. We measured stepwise the temperature at different power inputs. We measure the power supply of the inductor, which we can measure precisely. We are not so clear about the measurement of the high frequency input into the reactor. So we use always this DC input. And here we have the inactive state. The inactive state with 33 watt, we reach 280 degrees, and with 44, we reach 380 degrees. But with the activated state, we need only 23 watt for reaching this 280, and 30.5 watt to reach the 380 degrees. So we have an energy gain of 10 watt, the power gain of 12 watt. And I just finished an experiment with a nickel foil with definite composition. Just the preliminary tests showed that we have 44 watt gain. But that is, I will report later on. Then see the morphological changes on the surface is analyzed at the Swiss Nanoscience Institute at the University of Basel. They are well equipped, and the starting material is typically a shining material, which is used in the jewelry and watch industry, where I made this electroplating enlarged. We see that of course we have a different image on the surface, but the surface is covered completely, and with small exceptions and a few impurities. And then after the reaction, the material looks quite different. So if you see that difference here, it's the same magnification. We see that we have melting zones and scattered holes around. So these scattered holes is a strange phenomenon, because we can assume that and then, palladium is melting at 1,550 degrees, and our reactor was running at 200 to 300 degrees. So this is really a melting and recrystallization process around these holes. So we presume that these are hotspots, as mentioned by Professor Iwamura recently, and these scattered hotspots can be nuclear active environments. I come to the point D, energy dispersive X-ray analysis for done at the same institute in Basel for looking about the elements on the surface. We see that we have nickel and palladium on the starting material, so it's a small area which is analyzed. We have analyzed in five places, and then the reactive material was 2 probes on 5 places, and you see it's an obvious difference between the spectra. The summary of the analytical results shows that this gives an answer of the question whether it can be nuclear nature. And we have seen carbon also in earlier experiments where we have seen only carbon appearing. And here we have oxygen. Of course, oxygen is this 2.4%. That is why we have stored this raw material on air, whereas the reactive material is stayed always under vacuum and hydrogen. Aluminium appears on some places, on others we have no aluminium, and silicon also between about 1 and 6%. And the nickel appears to reappear, but this can be explained by the holes which the nickel is shining through. And palladium appears to disappear, but effectively it will be not consumed, but it will be displaced from the holes to the rims. And by the way, carbon, we have seen on these melting zones, on top of the melting zones, we have seen up to 50% of carbon. The morphological changes are similar to the picture I showed at ICCF26 in Szczecin, where we have seen little craters with carbon on top. So I come to the discussion. The temperature effect, excess heat, surface changes, and EDX analysis. We can speculate about the temperature effect, whether there is a plasma development and it may reach a saturation point, but this is a pure speculation. I have no idea. Maybe that somebody of the auditorium has an idea what the reason could be for this remarkable temperature kink. Then excess heat is repeatable within selected material. We have seen with ultra pure nickel, we have seen no effect. Maybe I have had not enough patience, because after 1,000 hours I stopped the experiment. So it's always long lasting, and the surface changes show that we have a local melting on nuclear and active environments. And the decay of palladium into carbon, oxygen, and silicon and aluminium, always smaller atoms. We have never seen copper, which is reported by other authors. And then I come to the question, what could be the reason for the formation of the Leonard products? Is it fusion or fission? I remember an impressive speech of NASA scientist Teresa Benio at ICCF26 in Poland. She asked, lattice confinement fusion, is it fusion, fission, or both? And she mentioned also nuclear disintegration, and that is probably exactly what we observe. We see only smaller and stable elements. And the explanation of this. Of course, it may be that in the medium there is a fusion fission process, but what we see finally is a disintegration. So we have no idea about the mechanism. But my favorite explanation is the structured atom model by Edo Kahl and co-authors. I think this is a revolutionary and very modern model. It's not a theory, but it is a visualization which explains many things which other models cannot. They see the nuclei as dense spherical packings of protons, and this can explain
5 minutes. 5.
The fractal structure. So they have had much criticism because they dispense with the neutron. But if you understand the neutron as an interaction between protons and electrons, then it is very meaningful. So the fractal deployment of the elements look like this. This is palladium, and palladium is composed of a number of other elements. For here, it's, for instance, the blue is carbon, and it decays in these different elements. So I come to the conclusion. The reactor is very useful for R&D. Of course, we have good ideas how to scale it up, but it is far from being optimized. So we have a lot of reserve. It is affordable, and it produces repeatable results, excess heat and transmutation. And this is the excess heat is irrefutable and repeatable. And let me make a proposal or a question. May atomic decay, what we have seen here via LNER, lead to a new avenue for treating radioactive waste? That would be a tremendous new field opportunity of business, which has not been touched now. At least it is worth to consider it, because we have seen this. If we have a palladium decay into smaller elements, this assumption could be conceivable. So I thank you very much for your attention, and I'm looking forward for your questions.
Okay. Very clear presentation. I want to make a question immediately. So, which one is the frequency of your inductor?
We started with 33 kilohertz and have seen eventually 8 hours lasting bursts of heat. And then we went to 100 kilohertz. And this is, of course, chosen very arbitrarily. We have not varied further, and we have not worked on the geometry. We should have a digital twin for optimizing these effects. But that is 100 kilohertz, 105 in the extreme.
Okay. Iwamura, please.
Okay. Thank you for your nice presentation. I'm glad to know that you also observed a significant oxygen increase. And my question, did you measure the isotope ratio of oxygen or carbon? No?
Oxidation.
No,
Isotope ratio of oxygen.
Oxygen, of course, we have seen oxygen. That is in two different materials. Oxygen appears when we have a palladium-plated nickel foil and palladium-nickel plated alloy nickel combination.
Okay. And did you measure the isotope ratio of oxygen?
That would be a very interesting point. That would be the ultimate proof that it is a nuclear nature. We have not, since we have only 200 milligrams on total of palladium in the reactor on 3.5 grams nickel, the amount of material is so low that we should have a method development for lifting off, but we have not a possibility.
Okay. And every time you measure the carbon increase or not, sometimes carbon increase was every time.
Carbon appears all the time.
Okay.
All the time when we have elemental shifts.
Okay.
Yeah.
Thank you very much.
So,
Yeah, this is very good, very interesting work, very smart.
yes.
Did you see any nitrogen in your analysis?
No, nitrogen we haven't seen. No.
Okay, because maybe there is also. Okay, thank you.
Maybe in the gas phase, but if
No, in the solid phase, no.
the solid, no, on the solid surface we haven't seen.
Okay, thank you.
Okay.
Thank you very much, Heinz, for excellent presentation. On slide 8, you showed holes. We've seen them in several experiments, but I have to give credit to Dr. Takaaki Matsumoto, who published palladium electrolysis experiment where inside the split electrode, he analyzed and found at crystal grain boundaries holes appearing. And I can even see from the SEM you showed via the stream that you have the holes appearing on the crystal grain boundaries. This is exactly what we have observed. And if you look at those with a higher magnification, I suspect you'll find what we found, which are little spherical objects with domed areas 8 around the outside of those, and it's actually like a carbon ball.
Question.
The question is, have you got access to better SEMs? Because you need a better resolution. If you haven't, that's okay. Carbon was observed by Matsumoto and Adamenko in all of their experiments. Have you seen my poster presentation from this ICCF?
Oh, so sorry.
Okay, so
Okay.
I agree with your assessment that it's cluster decay, totally and utterly. And just refer to Matsumoto's work and Adamenko's work. You'll see the same pattern that you saw in your data, in the historical data. And I believe it's vacuum cluster decay because of reducing vacuum pressure by the structures that do the work. So I'd like to speak to you if that's possible.
So we are working between 10 and 50 millibar, and the crystal boundary, that is an important issue because on one slide, we have seen in the magnification that these little scattered holes are along this probable crystal boundaries. Maybe that this is an important observation, and we should go with a better resolution behind this question.
Yes, Matsumoto holes on the boundaries, filling out and eating the whole crystal after a while. So see if you can see a progression from the boundaries to the whole crystal being consumed.
Okay, Bob, another question.
Thank you.
Maurizio?
Yes, thank you for the presentation. Just a comment on the last slide where you mentioned waste treatment. I don't know if you've seen someone has already tried that with success with cavitation. So if you haven't seen, look at Cardone Albertini treatment of nickel and cobalt and thorium, I think.
Yep. Yeah, but he was not working with high frequency. Maybe that this could be a pathway.
Yeah.
Maybe.
They have in minutes 11% reduction of radioactivity.
Oh. Thank you very much. I will follow.
You have my email because you sent me an email for the preparation. So in case I send you the material.
Yes.
Thank you.
Thank you very much.
Okay. Nobody more. Coffee break time. Thank you. Thank you, everybody.